continue on in chapter 7. Okay, so we've been talking about chapter 7, which is types of reactions and ways to classify reactions. And last time we talked about several different sort of classifications of reactions. And as we talked about last time, you can definitely classify kind of the same reaction in many different ways. So what we really looked at last time was sort of the big umbrella of redox reactions. And redox reactions are essentially oxidation reduction reactions. And basically what that means, as we talked about last time, is if something goes through an oxidation, it typically will lose electrons and it will become really more positive as it goes through that oxidation step. And whenever you have an oxidation step, you will always have a reduction process occurring as well. And that is typically when somebody gains electrons. And they obviously will become more negative as they gain those electrons. So we talked about also kind of a simple way to figure out if something is being oxidized or reduced. And you could use just a basic sort of number line. To the right, more positive numbers, to the left is negative. And really, if you just follow the path of the oxidation state, if it is becoming more positive or heading to the right, it is going through oxidation. And because when something gains electrons, it becomes more negative. If you sort of follow the path on the number line heading to the left, is going to be something that's going to go through reduction. And basically what we're talking about is really the oxidation states of the element. So when you look at the oxidation state on the reactant side versus the oxidation state on the product side, and as again is sort of the charge each of these elements would have in their sort of arrangement. And if you see it again becoming more positive, it's going through oxidation, becoming more negative, going through reduction. Not to be confused with what we talked about as well, I believe, which is what is known as oxidizing agent and reducing agent. So just a reminder that the thing that gets oxidized is also what is sometimes referred to as the reducing agent. And that, again, is always found on the reactant side of the equation, while whatever is going through reduction is also known as the oxidizing agent. And as we talked about last time, the reason their names are really like that is because that is essentially what they cause in the other element. So as it goes through oxidation, that means it's going to lose electrons. Once it loses electrons, it allows somebody to gain electrons and become reduced. And that's why the thing that goes through oxidation is known as the reducing agent, while the guy that is getting reduced is known as the oxidizing agent, because in order for him to pick up those electrons and gain those electrons, somebody has to lose electrons. So it causes somebody else to lose the electrons. So when we talk about the reducing agent, the oxidizing agent, sometimes it gets confusing for some people. The best way to sort of do it is just to think about it in this basically as opposites. So reducing agent is opposite of the oxidation, or is, you know, the thing going through oxidation. The oxidizing agent is the thing that is going through reduction. So kind of opposite of the names when we're talking about the agents, but again, not to be confused with what is being oxidized and what is being reduced. Now, as we talked about, again, the redox is sort of the big classification, kind of the big umbrella. And underneath that sort of umbrella, we talked about some different types of classifications as well. So for example, we had a synthesis or combination reaction. That's essentially when you take two things and kind of make one thing, so kind of put them together. And although it is a synthesis or combination reaction, overall it is also still a redox reaction in some of those ones that we looked at. We have the decomposition reaction, which is pretty much the opposite of combination. So in a decomposition reaction, you start with one thing and you break it apart into multiple sort of substances. Also, again, a redox reaction, but specifically can be classified as a redox reaction as well. In addition, we saw combustion reactions, and there's really kind of two types of combustion reactions. Essentially, anything that involves O2 on the reactant side technically could be classified really as a combustion reaction. But most of the time, what we think about a combustion reaction is more of the organic combustion reaction. And that's where we have something that's carbons, hydrogen, and oxygens plus O2, and it always makes CO2 and water. So if you see some organic guy plus oxygen, O2, it is a pretty safe bet on the product side. It's going to be CO2 and water as what is being formed. Now, those also are oxidation reduction reactions, as we talked about. And the last sort of classification was a single replacement reaction. And in a single replacement reaction, you basically have one element, maybe a metal, uncombined, no charge, or you have a non-metal, uncombined, no charge, plus an ionic compound, so something that's positive or negative. And what ends up happening is the guy with no charge comes in and kicks out one of those guys, either the positive or negative guy. If it's a metal that you're starting with, it will kick out the positive guy. If it's a non-metal, it will kick out the negative guy, and it will form a new ionic compound. And whatever element gets kicked out of that original ionic compound ends up by itself, uncombined, and also has no charge as well. So that's a sort of single replacement reaction. Again, in order for that reaction to take place, whatever is coming in needs to be more reactive than what it is replacing. If it is not, then you would not see that reaction actually occur. Again, single replacement reactions are also under the big umbrella of redox reactions. Any questions on any of those sort of classifications that we talked about last time? So I think this is where we sort of left off here. The next sort of really big sort of umbrella of types of reactions are really what are known as exchange reactions. And really more specifically, they're really known as double displacement reactions. And in a double displacement reaction, it has the general formula, as we would probably see, as A and B plus C and D. And the way you could recognize this as a double displacement reaction is both of these guys here are ionic compounds. So this is a positive and negative guy. This is a positive and negative guy. Again, you're starting with two ionic compounds. And what always happens in these type of reactions is basically the two positive guys will switch partners. So the two positive guys basically will switch partners. And the result of that is you get two new ionic compounds on the product side, so positive, negative, and C and B, which would be positive and negative. So we get the formation of basically two new ionic compounds on our product side. And again, this type of reaction is, again, sort of like the redox reaction, is sort of the big umbrella. And as we will see here very shortly, there's a number of sort of more specific ways to classify reactions that really do fall under this umbrella of double displacement reactions. So let us take a look at some of these here. Excuse me. As I mentioned, double displacement reactions are also sometimes called precipitation reactions. And that's a way that we can basically classify this type of reaction. And what makes it a precipitation reaction is you have the exact same reaction that we just talked about happening. But what ends up happening is one of these guys, in most cases it's just one, will form some type of precipitate, which is abbreviated PPT. So some type of solid is basically formed as a combination of what happens when those two ions come together. And that's why it's sometimes called a precipitation reaction, because ultimately you're making a solid as a result of that. And this usually happens, as we will see, when you take maybe two solutions and you pour them together. There are two solutions to begin with, no solid. But once you pour them together, what you're essentially doing is mixing all the available ions. And then there are certain ions that want to come together to make a solid. And we do see some type of precipitate form. Another very common sort of double displacement reaction is an acid-base reaction. And sometimes it's referred to as a neutralization reaction. And for the most part, as we will see, this usually involves an acid plus a base. And we typically make two things. We make salt and water. It's a general reaction. When you take a strong acid and strong base together, you make a salt and water. You may ask yourself, what is a salt? So a salt is really just an ionic compound. So you make some type of positive, negative guy coming together. And obviously water is H2O. And how we basically, in this reaction, as we will see, the really basic thing that's actually happening is we take the H plus from the acid plus the OH minus from the base, and we're basically forming water. So this is sort of really what's happening in this type of reaction. But ultimately, it is a double displacement reaction. The two cations are basically switching partners. But the main reaction is taking place typically when we do specifically a strong acid and strong base together is really the formation of water. Now, unlike a precipitation reaction where you could actually physically kind of see the precipitate being made, a lot of times you can't really see water being made, right? So you look at it, it may just look like the volume went up or something like that, but you don't get blinking lights in it that say, hey, we made some water or anything like that. So visually speaking, it is sometimes hard to recognize that you've made water. But whenever you essentially take an acid with a base, so if you could kind of recognize that, you will know that, you will end up basically with water being made. Again, not really a visual indication that that occurred, but it is definitely what is happening in this particular reaction. And if you remember, I think we talked about some driving forces for chemical reactions. And really, there's kind of three main ones, and that is a precipitate being made, the formation of water, and an electron transfer, which is all those redox reactions we talked about previously. So we're really going to focus in here on this part of the chapter on these two sort of driving forces for chemical reactions to take place, that precipitation occurring and also that formation of water. And again, you could kind of see, some of our classifications here of reactions. But again, usually this type of reaction and this type of reaction, which is what we're focusing in on, are usually under the big double displacement reactions, while obviously our combustion and all those other ones that we had are under our redox sort of umbrella. So as I mentioned before, here are those driving forces. And again, we're really going to focus in on this part with our double displacement, this guy, and really this guy as well. So a lot of double displacement reactions will result in a gas being formed. And it may result from a direct forming of a gas as a result of that double displacement reaction, or it may result in the gas being formed as a result for secondary sort of reaction that occurs that we will also see. Any questions on that so far? All right, so let's take a look at the first one, which really is a precipitation reaction. So as I mentioned, what essentially will happen is in a precipitation reaction, we have a double displacement. We have our two positive guys coming together to form a solid, and our two positive guys switching and making a new ionic compound that forms a solid. And as you can see here, we're really starting with a solution here. We're pouring a yellow solution. And in this particular case, we get this precipitate that is formed here. And this is maybe something like, if you took lead to nitrate, plus say maybe some sodium iodide. You could recognize this really as a double displacement reaction. This is a positive guy and a negative guy, positive guy and a negative guy. And if we wanted to predict what goes on the other side, the products, what's going to basically happen again is our two positive guys are going to switch partners. So the two positive guys will switch partners. So it's really important, especially if you have a reaction like this where you're not given the products, but you're just given the reactants, that you really do this in the correct order. And what I mean by that is we talked about balancing equations. And when we balance equations, we want to change just the coefficient that's there in the front. But very often what people will do is they'll try to balance and write the formulas, what's going on the other side. And they usually will end up with the wrong formula. Things won't balance because of that. So the best thing to do when you're getting to that part of, I want to figure out what's on the product side, is to really just break this guy up into its basic units. So this is lead 2 nitrate. That means we have a lead with a +2 charge. And even though there's 2 nitrates, for trying to figure out what goes on the other side, we just want to think about the basic 2 parts of it. And nitrate is a -1. Now over here, our sodium, the basic unit of that is sodium with a +1 charge. Basic unit of this is iodine with a -1 charge. So what we know is going to happen here, now that we have the basic units, and again, you can see I'm not concerned about the extra 2 here at this moment. Now that we have these guys, we want to put them together properly, like we did with nomenclature. So my positive guy is going to switch partners. So we're going to end up with these 2 guys coming together on our product side. So when we take lead that has a +2 charge and iodide, which has a -1 charge, just like in nomenclature, the correct formula should look something like this, PbI2. When we take sodium that has a +1 charge and so nitrate that has a -1 charge, we just need one of each of those. So the correct formula here would look something like this. Very common people, when they have to predict the other side, go, oh, I got a 2 here, so let me start throwing some extra 2s on the other side and stuff like that. And you definitely don't want to do that. So the order at which you want to kind of do these type of things is you want to get the basic units of those ions on the left-hand side, switch the partners, and put them together correctly based on their charges, just like you would do in nomenclature. Now that you have all of the correct formulas down, you then could go and balance. So we can then at this point put a 2 in front and a 2 in front. And we will now have really a balanced chemical equation with all the right formulas. So again, sometimes people really mess up on that because they try to do both things at once. So they try to balance and write the formulas. And usually it doesn't end up well because you end up with the wrong formulas. Question first off on that there. Now, and that is a basic double displacement. So you can basically see we switch partners. So positive guy went to the other guy. This positive guy ended up with the other negative guy. And that is basically what happens in all double displacement reactions. Now, what happens on this side is we do get a solid that's formed. And in this particular case, it is this solid right here. It is the lead 2 iodide, which, by the way, is probably that yellow that we're actually seeing in this particular example. It actually makes this nice yellow solid. I think we'll see it next week when we do that experiment on Wednesday of next week. But it makes this yellow solid that's basically formed. So ultimately, this is a double displacement reaction. It is more specifically called a precipitation reaction because we made this solid here. Any questions on that there? Okay. And I think that's what it says underneath my scribble, that it's a precipitation reaction. All right. So well, we'll see if it plays. I'm not sure.
If we mix an aqueous solution of silver nitrate with a solution of sodium chloride, the products are a precipitate of insoluble silver chloride and water-soluble sodium nitrate.
So as you can see here in this one, we started with really 2 solutions, no solids. But when we mix those 2 solutions, the mixture of those ions, when they come back together, one of those combinations makes a solid. So this was silver nitrate, which is aqueous, which means it's a solution, no solid, plus some, I forget what she said, I'll go with sodium chloride. Sodium chloride in this case, also a solution, no solid. And again, we can recognize this as a double displacement reaction, positive, negative guy, positive, negative guy. Again, we could take the same approach. This is basically silver with a +1 charge. This is nitrate with a -1 charge. our sodium over here is +1, and our chloride is -1. So again, in our double displacement, our positive guys are going to switch partners. So these guys come together, and again, these guys come together. And just like before, if we want to predict what happens on the other side, we want to put them together just like with nomenclature. So silver is a +1, chloride's a -1. So you just need one of each of those guys. Sodium also a +1, and nitrate a -1. So again, you just need one of those. And as we'll learn here very shortly, based on solubility rules, it is actually that silver chloride that's coming together to form this white solid, as you see in this reaction. In this case, we wrote the proper formulas, and if we take a look at it, it is actually balanced at this point as well. We've got one silver on each side, one nitrate on each side, and also one sodium on each side, and one chlorine. This is also a very good sort of demonstration, as you can kind of see there. Sometimes when people think about a solid being formed, they think like it's got to be like a rock hard solid that kind of comes in and drops all the way down, to the bottom of the test tube or the beaker or whatever it is. As you could kind of see here in this little animation video, it doesn't necessarily have to be rock hard. It could be something like we see here. It starts to get cloudy. There's some white solids kind of floating around, some particles that was not there to begin with that basically developed as you mix together these different sort of solutions. By the way, if you took this test tube and centrifuged it, so when you centrifuge something, it spins really fast. Basically, all that solid would come to the bottom and really compact down. You'd be able to see the solid, obviously a lot better and stuff like that. And when you would do that, you would see that when you looked in that, if you did kind of centrifuge it, you get that solid on the bottom, which is obviously the white solid, which would be your silver chloride, and really still floating, because this is an aqueous thing, still floating in the solution part is really your sodium ions and your nitrate ions, and kind of the liquid part of what would be left there is really where the other product is. And because it's really sort of a strong electrolyte, as we'll talk about, it's really not staying together. You basically have those ions that are floating around in that solution. Any questions on that there? Okay.
Silver ions react with chloride ion.
I think I mentioned that there. All right.
A solution of ammonium sulfide is added to a solution of lead nitrate. A precipitant forms.
So again, we see that from a mixture basically of two solutions making that solid. And again, it's those ions, when they switch partners, one of those combinations does make a solid. And we're going to talk about here just a second here how we know what combination really makes that solid and which one doesn't. And there's things that are known as solubility rules that we could kind of look at and determine, oh, when we put these two guys together, we would expect a solid to form. If we put these two guys together, we wouldn't expect perhaps a solid to form. So that brings up the idea of solubility. And when we kind of look at solubility rules, it's usually kind of three sort of classifications in terms of sort of solubility when we kind of look at these rules that help us decide, what will make a solid, what will not make a solid. If something is determined to be soluble, that pretty much means that if you have a solid and you put it into a liquid, the solid will dissolve completely. So it will basically mix really well. Also means if you put two liquids together, it will mix and it will look just like one liquid in there. You wouldn't see any type of layers. And if we determine based on solubility rules that something is soluble, those guys should get the aqueous symbol. And the aqueous symbol is what we use for solutions that everything mixes together really well. I think we also talked about this last time, but just a reminder that the difference again between a liquid, something that has that L symbol, and something that has that aqueous symbol is if you have the L symbol, it is just one sort of substance by itself. So the example I think I used last time is if you had just pure water by itself, nothing in it, just H2O in there, that would be considered a pure liquid and would get the L sort of designation there. Now, if you take something like water and then you put something else in it, like some sodium chloride, you will get a sodium chloride solution. And the sodium chloride solution will have that aqueous symbol next to it as opposed to water. So if you took some water and you took some solid sodium chloride and put them together, you get a solution that has that aqueous symbol. So that's, again, the difference between aqueous and liquid. Now, if something is insoluble based on solubility rules, that means that the solid will not dissolve in the solution. Also means if you have a couple of liquids or something that you're mixing and they're insoluble in each other, you will see layers. Basically, they will layer out from each other. If you put two liquids that are insoluble in each other, sometimes referred to as being immiscible, and you see these different layers that happens. And anything based on solubility rules that say it is insoluble, those are guys that should get the solid symbol next to it. So like before, our PBI2, when we see the solubility rules, it will tell us that it is insoluble in each other, and it's the one that should get the solid, just like as we just saw there earlier, our silver chloride, when we put those two ions together, makes something that's a solid as well. Now, there is sort of a third classification that sometimes occurs with solubility rules, and that is what is sometimes referred to as being slightly soluble, sometimes abbreviated like SS, slightly soluble, on a sort of table. And usually when we talk about something being slightly soluble, we oftentimes think about it as being more insoluble. So for us, if something is sort of listed as slightly soluble, you would also use the solid symbol for it as well. So again, that slightly soluble leans more towards insoluble. So I will tell you that the truth on this is, even though we look at solubility rules and perhaps something tells us that something is insoluble, it doesn't necessarily mean that 100% of the time that's the case. If you continue on to 1B, you'll learn that there's a lot of factors that affect sort of solubility. And sometimes even when we think about something as always being soluble, everything has some degree of sort of solubility or being soluble. So even things that are technically insoluble, there's a very small, minuscule amount that will actually dissolve. What symbol are used for two liquids that form two layers? So this would be insoluble. What it would probably be in that case, because you have two liquids, you would still use the L's for each of them, and they just wouldn't mix. So we typically don't use the S for liquids when they're together, if we're kind of just talk about two liquids. But in general, when we talk about liquids in terms of not mixing, is sometimes referred to as being immiscible, which is like a way you could say insoluble for two liquids. While if something's soluble and it's two liquids, miscible is sometimes used. But usually we'll just use these type of things, and really we wouldn't use any type of sort of symbol for those liquids other than probably L if they were pure liquids, again, because there's really no solid being made. So usually the S there is referred to something that will kind of make a solid when they put together. Other questions? So when we look at solubility rules, as we'll see here on the next table, and here are some of the general solubility rules. Basically, the idea here is if you could determine it is soluble, when you write the formula in an equation, you should give it the aqueous symbol. If something is determined to be insoluble, those are the guys should get the solid sort of symbol next to it. So let's talk about some of these rules here. Most nitrate salts are soluble. Pretty much nitrate is soluble in everything. So what that means is as soon as you see something with nitrate in it, it's pretty much going to get the aqueous symbol. You pretty much don't have to go any further than that in terms of the formula. It definitely will be aqueous. Things from group 1 on the periodic table. So guys from group 1 on the periodic table and ammonium are soluble in everything. So they are soluble in everything. There's no exceptions here. So again, if you see anything like a sodium in a formula, a potassium, a lithium, they are always going to be 100% aqueous no matter what the situation. They all should get that aqueous symbol. Also, if you see ammonium, which is that NH4 plus in a formula, always going to be also soluble, so it should get that aqueous symbol. Now, most chlorides are soluble, and in addition to chlorides here, in addition to chlorides, bromides, and iodides are all the same there. Any of those halogens, for the most part, chlorine, bromine, iodine, they are soluble in everything. But there are three exceptions. And the three exceptions is when one of those guys hooks up with silver, lead 2, or mercury 1. So those are three exceptions, which means if you have chloride, bromide, or iodide in a formula, you should give it the aqueous symbol, except if it has in that formula with it silver, lead 2, or mercury 1. Then it goes from being aqueous to being insoluble or a solid. Most sulfates are soluble. There are some exceptions. Barium sulfate, lead 2 sulfate, and calcium sulfate. So most of these guys are soluble, which means they should get the aqueous symbol. But if you have one of these exceptions, they should get the solid symbol that's going on. Most hydroxides are only slightly soluble. So again, that leads to more like insoluble. And the exceptions are group 1 and barium and calcium, which are moderately soluble. So exceptions would be like group 1 involved. And again, if they are typically solid, they would then become aqueous in those exceptions. Most sulfides, carbonates, phosphates are only slightly soluble. So usually these guys get the solid symbol next to it. So I think we have another sort of version of it. And again, this is again something that they want you to memorize. So for future classes, so make sure that you do that. So we'll stay with that. Also, you could add chromate to that. Again, is something that's typically solid. There are a few exceptions. Again, some exceptions are our group 1 and our ammonium. So those are some exceptions. Question on that there. Here's another sort of version of it, which might be a little bit easier. Again, our nitrates are soluble, no exceptions. Group 1, basically an ammonium, also no exceptions. And then here's our chloride, bromide, iodine with our 3 exceptions. So if you find yourself over here on the purple side, it is going to become solids. Kind of on the yellow side, it will become aqueous. And again, here, these are things that are typically insoluble, which means these guys in the light blue are typically solids, except for if you get over here, then they become aqueous. So again, how do we sort of determine this works or not? Let's just take that example that we saw earlier. We had our silver nitrate plus sodium chloride, making our silver chloride plus our sodium nitrate. So if you were going to use these sort of solubility rules to determine what is a solid and what is not a solid, here's sort of the approach that you want to do. Now, sometimes you may not be able to find both things on the table, but you can find at least one of them in most cases. So although we may not find silver as a main thing on the table, we do find nitrate. And what we know about nitrate is it is pretty much soluble in everything. There's really no exceptions. So as soon as we see that nitrate, we know this guy should get the aqueous symbol next to it. Now, when we go to sodium chloride, we can actually find both of those things on the chart. Sodium is group 1, which is here. So this is like group 1. And really, because there's no exceptions, you actually could stop at that point and you know that it is going to be aqueous. Now, if you weren't convinced by that, you could go to the second one, which is the chloride. And we do find the chloride here, and it's soluble in everything except silver, mercury 1, and lead. And that's not the case here. So that also tells us that this guy should be aqueous. When we go over to silver chloride, again, the chloride is soluble in everything except when it hooks up, for example, with silver, which is the case in this case. So normally chloride would be soluble, but because this is an exception, this is how we know this is the guy that becomes the solid. And lastly, if we look at the last guy, we have sodium, which is soluble in everything. Nitrate also soluble in everything. And that's how we know this guy gets our aqueous sort of symbol. And that's how we know in this case, this precipitation reaction, it is the silver chloride that is making the solid. Question on that there. And again, if we sort of look at the other one that we put together, which was also the lead 2 nitrate plus our, I think I used sodium iodide, went to our PbI2 plus our NaNO3, put a 2 there and a 2 there, I think. Same approach. When we see the nitrate here, that's enough to tell us there's no exceptions. He should get the aqueous symbol. Truthfully, as soon as we see the sodium, that is enough to know that it should get the aqueous symbol. Now over here, we may not find lead, but we do see iodide. Again, iodide is soluble in everything, which means it should get the aqueous symbol, except it is in this case hooked up with an exception, which is lead. So that goes from being aqueous in this case to being solid. And again, that's that yellow solid that we saw previously. And same thing here, we could look at sodium, and that's pretty much all you need to look at. You could also look at nitrate as well. Both of those things are soluble pretty much in everything. So again, they do want you to kind of know these solubility rules going into the remainder of your classes. So we will stick with that. So make sure that you do memorize these sort of rules. Any questions on how to use those rules there? All right, let's see some more examples, I think.
All nitrate salts are soluble. Lead nitrate solid is added to a half-filled beaker of water. A magnet is placed in the beaker, and this is placed on a magnetic stirrer. The crystals dissolve in a matter of seconds.
So you can see they're solid, so soluble.
And ammonium salts are soluble. An example is potassium iodide, which is added to this beaker of water. When placed on the magnetic stirrer, the crystals dissolve immediately. Chlorides, bromides, and iodides are generally soluble, with the exception of compounds of mercury, silver, and lead. Potassium iodide solution is added to a lead nitrate solution. The precipitate that is formed is lead iodide. An alternative method to precipitate lead iodide is to use a pipette to deliver the potassium iodide.
So obviously you can see that is becoming insoluble in this particular case. All right, so let's take a look at these. So why don't you take a second here and decide which of the following ions, when you put it together with lead 2, will be soluble in water. So think about the solubility rules we just saw and think which combination will be soluble. So that means that we would not get a precipitate form. Okay, so let's take a look and sort of decide here. So if we put lead together with sulfide, sulfides are pretty much insoluble. The only exception would be if you had maybe some type of group 1 metal, which you don't. So this guy we would expect to make a solid. Now, when we put the lead together with chloride, chloride is soluble in everything except silver, lead, and mercury 1. So in this case, that would be an exception. So instead of being soluble here, we would expect it to be insoluble and a solid to form. Now, when we put the lead together with nitrate, we're pretty much good to go because nitrate is soluble in everything. So we would expect this to be aqueous. So remember, pretty much your guys that are soluble in everything, no exception, group 1, anything with nitrate. Also, by the way, acetate, you could add to that list pretty much, which is CH3COO minus or C2H3O2. So these guys are pretty much soluble in everything. So again, if you see those guys, you have a pretty good shot at it being aqueous. Lead coming together with sulfate. Sulfate is soluble in everything, but there are some exceptions, and one of the exceptions would be barium in this case, and also lead. So those are a couple of exceptions. So this guy would be solid, and sodium is soluble in everything, and that is lead, which is 2 positive guys coming together, which hopefully we know does not happen, right? So the 2 ions that are positive won't come together, right? Opposites attract, things with the same charge go apart from each other. So we would not get it to come together at all in that particular case. So it looks like the correct answer here is C. Any questions on that there? Okay, so which compound would be expected to be insoluble in water? So take a second here and try to decide. So we're looking for the one insoluble, which means we would expect a solid to be formed here. Okay, so let's take a look and see. So again, just sort of dissect these things. When we look at this guy here, as soon as I see that sodium, I know there's no exceptions. So I know this guy would be soluble and would be aqueous. Now, when I look here, although I may not be able to find gold there, I can find sulfide. And if you look back at your sulfide, it is insoluble. Maybe the only exception would be something from group 1, which is not the case here. So we would expect this guy here to make a solid. Again, look at the third one. We may not find copper there. And as I mentioned a second ago, you should add acetate to your list there. Acetate is soluble in everything. So this guy would be aqueous. So again, if you sort of added your acetate would be sort of over here in your soluble guy. Soluble pretty much in everything, acetate, which is that polyatomic ion. So whoops. So we're here. Coming here, as soon as we see ammonium, which is NH4 plus, also soluble in everything, so we are good to go. That's going to be aqueous. And lastly here, may not find calcium necessary there, but we will find Br. And Br is Br minus, which goes with Cl minus and I minus. And they are soluble in everything, but there are 3 exceptions. And that is silver, lead, and mercury. And in this particular case, that is none of them. So this would then be still soluble in that case. So it looks like B should be our right answer there in terms of which one should be insoluble or make a solid. Question on how to kind of dissect those guys. Okay, let's try one more here. Here we're looking for which one would be soluble. So no solid in this case. So take a second here. Okay, so same sort of dissection approach here. Looking at a first one, again, we see chloride, as we talked about a number of times. They're soluble in everything except one of the exceptions is silver. So we would expect this guy actually to be a solid. Hydroxide, excuse me, is typically insoluble, except if it's group 1 or barium and stuff like that. So this guy as well, we would expect to be a solid. Again, that can be found on the bottom, I think, in the blue section of the last solubility table. We look at phosphates there. Phosphates as well are going to be insoluble. So this guy should be a solid. Again, on the bottom blue little box on that second solubility table. Looking here, hydroxide, also on the bottom in terms of it being a solid, but an exception to hydroxide is pretty much normally going to be solid. Exception would be anything from group 1, for example. And group 1 on the periodic table does include potassium. So instead of being a solid, this guy would become aqueous. And lastly, we have our sulfate, and our sulfate is normally soluble. Again, an exception to that is barium, lead, and calcium. So in this case, since we do have barium as the exception, it is not going to be soluble, but it's going to be insoluble. So it does look like D is the example there. Any questions on that there? How to use the table? All right. So how does this help us sort of understand what's happening when, for example, we mix together a couple of solutions that produce a whole bunch of ions in solution? The production of ions also does cause sort of another property that we see, and that is what is sometimes referred to as electrolytes. And electrolytes are basically substances that, when they're dissolved in water, they basically conduct electricity. And the reason they're able to conduct electricity is really because of the presence of the ions. So as the ions are becoming formed in the water or the solution, there's a lot of positive charges moving around. There's a lot of negative charges moving around. And that sort of helps complete the circuit, if you will, and is able to conduct electricity very well. So an electrolyte is really a substance that can produce ions in solution. It is the presence of those ions which helps us understand, if it can conduct electricity or not conduct electricity. And as we will see here in just a second, there's really 3 sort of classifications of electrolytes. There are strong electrolytes, there are weak electrolytes, and there are really non-electrolytes. As we will see, a strong electrolyte pretty much 100% breaks apart into ions. So when you have a solution that's a strong electrolyte, it basically will produce a lot of ions really quickly. And as we can kind of see here, with the presence of those ions, if we take like a light bulb hooked up with some electrodes, for example, the light bulb will shine very, very brightly because it's going to be able to conduct electricity really, really well. A weak electrolyte, as we will see, will essentially stay together, but will form some ions. So some ions will get formed in a weak electrolyte. And if you kind of hook up the light bulb example, not really super bright, not off, but kind of in the middle, you get like a dim light. The light bulb would go off a little bit because there are a little bit of ions floating around. So it's able to conduct electricity a little bit but nowhere to the extent of a strong electrolyte. A non-electrolyte, as we'll see in a second here, pretty much does not produce no ions. And that's important because it doesn't produce any ions. There's no ions in the solution. No ions in the solution doesn't help conduct electricity. And we see the light bulb does not go off in this particular case. So there's sort of three sort of parts to electrolytes: a strong electrolyte, which 100% breaks apart. Weak electrolyte mainly stays together, as we'll see, and a non-electrolyte doesn't break apart into any ions. So
a 400 milliliter beaker contains water. A small sample of potassium dichromate is added to the water. The solution is stirred, and all of the solid dissolves.
So I was waiting for more than just that, just so you know, but I was surprised. But what basically happens, though, what I think they're trying to show you here is essentially when we do have an ionic compound, which is a solid, what basically happens is you basically have a network of positive and negative guys together in a very ordered fashion. And basically what happens is a water molecule, which is polar, which means the oxygen is more negative, hydrogen is more positive. It will essentially come in and start plucking off basically these guys. And when it does, as I think we might have talked about in an earlier time, but basically the water molecules will then surround the ions. So the negative side of water will surround the positive cation, while the negative ion will be surrounded by water as well, but it would be the hydrogen side of water, because again, hydrogen is more positive in water. And that's when it disappears, if you will. So it disappears, the solid, and it really doesn't disappear. It just gets caught up in all the water, basically, and we can't physically sort of see it anymore as it basically gets dissolved into the water matrix. What do we usually do when we put a solid in to dissolve it? Exactly what we just saw there. Typically, we, kind of stir it. And as we're stirring it, we're basically throwing a ton of water molecules all over here, increasing the surface area. We're also adding a lot of energy, and that helps it dissolve a lot quicker than if you just dumped the solid in there and just kind of waited for nature to happen, right? It's going to take probably a long time. You usually got to give it some type of mix, right? Some type of shake to help it basically go through that dissolving process. So that brings us to electrolytes. So again, these are the three types of electrolytes, as I mentioned earlier. We have a strong electrolyte, which 100% breaks apart into ions. So if you did take something like sodium chloride that is in a solution, or a solution of sodium chloride, in the actual solution itself, it will 100% break apart into sodium ions and chloride ions. So 100% of what you got going on is that sodium ions floating around in that solution, chloride ions. You have absolutely none of these guys still together. And that goes for anything that's a strong electrolyte. Some acids, like hydrochloric acid, is a strong electrolyte. So when you put something like hydrochloric acid into solution, it also 100% breaks apart into these ions. And you have none of these units still together. And that's why these guys are also considered strong electrolytes, because 100% of it is ions. You produce a lot of ions very quickly. And same thing here, we produce these ions very, very quickly. And that's different than if we have a weak electrolyte. In a weak electrolyte, we have a little bit of the ions coming apart, but it mainly stays together. So if we take something like hydrofluoric acid, that is a weak acid. And when it breaks apart, we will get H plus and F minus. Different than a strong electrolyte is in solution, this is mainly what you have. But you have a little bit of these guys, so you do produce a little ions. And because it's able to still produce a little bit of those ions in solution, it's still able to conduct electricity. So here, as I mentioned before, the light bulb example will be very dim, as opposed to a very bright light bulb that you would have in a strong electrolyte. Now, in non-electrolytes, as I mentioned before, they will dissolve. They will not produce any ions. And again, because they don't produce any ions, it will not conduct electricity. So the light bulb will not go off. So an example of that is sugar. So for example, sugar is basically carbons, hydrogens, and oxygens. And that is going to be covalently bonded together. So when it basically goes into solution, it still stays together. And we get sugar that will dissolve. But because basically sugar is made up of all those nonmetals, we don't produce any ions when it dissolves. And because we don't produce ions, we don't get the electricity being conducted, and the light bulb basically will stay off. Now, a good way to recognize a difference between, say, a strong electrolyte and a weak electrolyte is if you were given the equation, in a strong electrolyte, it's a one-way arrow. It is pretty much heading towards the products. Everybody's breaking apart. Typically, in a weak electrolyte, you see arrows heading in both directions, a reversible type of reaction, which means there's a forward direction where the reactants go to the products, and there's a reverse direction where the products go to the reactants. So you have both directions happening at once. At some point, the rate at which it goes to the forward direction will equal the rate at which it goes to the reverse direction, and you'll hit what is known as chemical equilibrium. And that means that, again, as fast as it goes to products, it goes back the other way just as fast. And chemical equilibrium is also known as Chem 1b. That's pretty much all you talk about in Chem 1b. So when you get to Chem 1b, you'll talk more about really sort of these reversible reactions. But that's a very good way, especially if you see those two arrows heading in both directions, that usually indicates that something is a weak electrolyte, and it will mainly stay together. Any questions on that there? So how does this affect when we sort of dump things into solution? So what this affects when we dump, say, two solutions together that has ions. All right, so we got some positive and negative guys coming in. We got some positive and negative guys coming in, maybe from two different solutions. If it is a strong electrolyte, what that means is in solution, we would expect all those ions to be separated. Now, if it was a weak electrolyte, when you dump it into solution, you would expect that guy to stay together pretty much, but maybe a couple of ions floating around. And we would mainly have those guys basically staying together. So when we think about truly what's happening, in a weak electrolyte, it's really that guy staying together, but a few ions are coming apart. All right. So let us talk about this here. Which of the following statements is true? So take a second and read through them. I will as well. So let's see. If a substance is soluble, it must be an electrolyte. And that is not the case, right? Because something like sugar is definitely soluble, but sugar is a non-electrolyte. So that's an example of something that will dissolve, but will not produce any ions. So it's really not an electrolyte. If a substance is an electrolyte, it must be soluble. And that is true. So it has to have some degree of solubility. So a strong electrolyte will 100% break apart into ions. A weak electrolyte will also break apart into ions. So it does have to have some degree of solubility where it will dissolve at least a little bit in the case of, say, a weak electrolyte. Weak electrolytes must be less soluble than strong electrolytes. That's not necessarily true either. Non-electrolytes are non-soluble or insoluble, I guess is probably the word they're trying to use. Again, as I just talked about earlier, sugar is an example of a non-electrolyte, and obviously it does dissolve, so it's soluble. So it looks like perhaps B here would be the right answer there. That one is true. Okay. So let's take a little closer look at precipitation reactions and sort of what is going on when we look at these precipitation reactions. So here we have our barium plus our chromate, making our barium chromate. So they did want you to add chromate, I think, to your list. So that is going to be a solid that's happening here. And this is what is really referred to as the net ionic equation. And if we look at the molecular equation, which is when we take K2CrO4 plus BaNO3 2. And if we take these guys here, let's move some stuff out of my way so I can actually see. Let's do that. If you weren't sure what's happening here, we could look at this and we see this is a positive negative guy. This is a positive negative guy. And what that means is a double displacement reaction. So we're going to get two new ionic partners on the other side. So we want to think about these things in terms of what the basic units are. So the basic unit here is potassium with a +1 charge and chromate with a -2 charge. The basic unit of this guy is barium with a +2 charge. Basic unit here of this guy is nitrate with a -1 charge. Again, not interested in the extra 2s I have at this point. I just want to get the proper formulas in there first. So they're going to switch partners, which means the potassium will come over here to our nitrate. The barium then will hook up with our chromate. And what we should get on the other side is KNO3, not K2NO3, 2, which is what people commonly will do, again, because they're trying to balance and write the formulas together. The other thing that will come together is the barium that has a +2 charge and chromate, which has a -2 charge. That would give us our barium chromate. And based on solubility rules, again, we see potassium here is aqueous. Nitrate's involved on our second guy, so that is going to be aqueous. Potassium is soluble in everything. Nitrate's soluble in everything. And our chromate, again, going to be insoluble in this case. But now that I have all of the correct formulas down, what I want to do is balance the equation. So again, that is the order at which you want to do that. So now that I do that, I can balance it simply by putting I could write it 2 right there in front. And this equation here, where we write everything that is going on with their proper formulas, this again is what is referred to as the molecular equation. Any question on that there? So how we get to this net ionic equation, and I'm probably jumping the gun here, but since it's here, we'll talk about it. When we take our molecular equation, although it does adequately sort of describe what you mix together, sort of the reaction that's taking place, it doesn't really show you truly what is happening when you dump those two solutions into the same beaker. So we could take this molecular equation and we could break it up into what is truly happening in this reaction. And we could do that by taking whatever is considered a strong electrolyte and break it apart. The only things that we don't break apart would be things that are weak electrolytes, things that are solid, things that are liquid, and things that are gas. So these things we would keep together. Anything else we could essentially break apart. So potassium chromate is a strong electrolyte. Almost all ionic compounds are strong electrolytes. And that means when we break this apart, we actually have bigger screen. Okay. So we have, put it there. So we have 2 of the potassium ions and 1 chromate ion. And this is really what we have going on in solution from our first guy. Our second one, which is barium nitrate, will also break apart, and it would form a barium ion and 2 nitrate ions. And as you can see, the 2 here comes to the front when we break it apart, just like the 2 here came to the front when we broke it apart. And going to the other side, our potassium nitrate will also be a strong electrolyte. That 2 that's in the front gets distributed to each of the ions that are behind it. So that would break apart into 2 potassium ions and 2 nitrate ions. And again, that is the 2 here being distributed to both of those ions when we break it apart. And lastly, we have our solid, which would stay together as our barium chromate. What we have here is what is sometimes referred to as the total ionic equation. Or I think your book might call it the complete ionic equation. And really what this equation describes is truly what's happening when we dump in both of those solutions together. We get all these ions basically in the beaker, as we can see in the picture, floating around. And when we write our total ionic equation or complete ionic equation, you should always be able to look on both sides of the arrow and see some ions that look exactly the same. So if we look in this case, I have 2 potassiums on the left-hand side. I also have 2 potassiums on the right-hand side. They look exactly the same. I also have 2 nitrates on the left-hand side and 2 nitrates on the right-hand side. They also look exactly the same. These guys here, which are in boxes, these are what are known as spectator ions. So in this example here and here. And a spectator, right, if you basically do the definition of a spectator is somebody that is basically just watching. And that is essentially what is happening here. These ions are really there just to balance out the charge. They're basically just watching what's going on. They're not involved in actually the product that is being made in this reaction. So what we do with our spectator ions is, in our total ionic equation, we cross them out. And once we cross out our spectator ions, we are left with a third type of equation, which was the original equation up on top. It is really what's happening here is the barium ion is coming together with our chromate ion to form this solid that we see in that beaker on the right of barium chromate. And this equation here is as what I wrote up on top. This is what is known as the net ionic equation. So the net ionic equation really just cuts way down to exactly the main reaction that is happening here. And in a precipitation reaction, the net ionic equation will tell you basically what ions are coming together to form that solid. The potassium in this case, the sodium in this case, again, they're just spectator ions. And in reality, if you kind of look at this picture on the right, they're basically floating around up here. You know, they're floating in the solution part. And down here in this solid part, this is where we have our barium chromate. It's our solid down here. And so we have these ions. Again, they're really just there to balance out charge, not really forming any product. It is really just the barium that's forming it from the barium nitrate and the chromate from the potassium chromate that is forming that. Any questions on that there? Okay. So those are 3 really important types of equations that we commonly write for double displacement reactions. And again, a reminder, the molecular equation is everybody written with their correct formulas. The total ionic equation or complete ionic equation is breaking apart all of our strong electrolytes. Again, if it's a weak electrolyte, if it's a solid like we did here, are if it's a liquid or a gas, we keep those things together and we do not break them apart. And then we can find our spectator ions, which again, those ions should look exactly the same on both sides of the arrow. And if you do everything correctly in terms of balancing, you should have the same number of those ions on each side of the arrow, and they should kind of cancel out completely. And what you are left with is the net ionic equation, which basically tells you right to the heart of the matter, this is exactly really what's happening here. This is exactly the reaction that's taking place. Question on any part of that there? Okay, so let's take a look at some of this here. So again, we could kind of use our sort of solubility rules to help us decide some of these things here. For predicting solids here, we want to look at our solubility rules and help us decide which one would be a solid. Again, it could be one of these two things, but as we talked about before, as soon as you see that potassium, you pretty much know that's going to be aqueous. And then obviously our chromate going to be insoluble. So that is the guy that should get our solid in this double displacement. Again, sort of a decision tree there, our switching of partners and using those solubility rules. Any questions on that one there? And here's, I think we did this one as well. So we'll just kind of look at it a little bit quicker here. Again, same idea here. Chloride soluble in everything except for one of the three exceptions, which is our silver. And again, that's why it becomes insoluble and gets that solid. And as we talked about here, if we were predicting what's going to happen here, we want to predict the other side. We want to just take the basic units like we kind of done before. Again, the basic unit of potassium is a +1. Basic unit of sulfate is -2. Basic unit here of barium +2 and chloride -1. Again, even though there's some extra 2's there, not concerned with it at this moment. Want to just switch our partners and put them together with the proper formulas. So again, that should give you some KCl, and then we got there barium sulfate. And in terms of solubility rules here, again, as soon as you see that potassium, that is going to be aqueous. When you look at the sulfate, it is soluble in everything except for barium, again, an exception. So this would be our solid that would form here. Again, now that we have the proper formulas, we could take care of the balancing by putting a coefficient up in front. Maybe I guessed right as to which way they'll put it up there. No, but there you go, right? Based on our solubility rules there, our barium would be insoluble. Any questions on sort of those so far? Now, what happens if you have two ionic compounds and in a solution and you dump those guys together and you look at something like our next example here, maybe ammonium chloride. So again, if you break this apart, and we know this is a double displacement reaction, positive, negative, positive, negative. So this is going to be NH4 plus and Cl minus. This guy, again, basic unit is calcium. And even though there's two nitrates here, the basic unit here is nitrate. So again, we're going to switch partners. And when we put calcium and chloride together, we get CaCl2. Again, we need two of the chlorides to balance out the charge. When we put ammonium and nitrate together, we just need one of each. And at this point, we could do some balancing. So let's see here, perhaps a 2 here, maybe a 2 there as well. And we want to look at solubility rules. So we see chloride, and chloride is soluble in everything except for lead, silver, and mercury. And that is not the case here. So that means this guy is going to be aqueous. Ammonium is soluble in everything. You don't need to go any further. but nitrate could also give you the same answer. And that guy would also be aqueous. So what does this mean if we get two things on the right-hand side where everything becomes aqueous? We could actually use our net ionic equation to help us figure this out. So as we just saw there, let us go through those three types of equations. So we just did our molecular equation. Which is what we have up here. Now, if we were to write our total ionic equation, we would break apart everybody in there that is a strong electrolyte. So we would get 2NH4 plus 2Cl minuses. Again, the 2 would distribute to both of those guys. Our calcium nitrate would be calcium with a +2 charge. The 2 would come in front of the nitrate there and give us this. Again, the 2 would come to the front. I'm just going to go down here since I'm running out of room on my screen. On the right-hand side, that is also aqueous, which means that guy would break apart into calcium and a couple of chlorides. And our last guy, also a strong electrolyte, would break apart into a couple of ammoniums and a couple of nitrates. Oops. And a little extra scribble for good measure there, right? Let's get rid of that. Okay. Now, this again would be technically our total ionic equation. Now we want to look for spectator ions. Well, I have 2 NH4 pluses on the left and 2 on the right, so they cancel. I have 2 chlorides on the left and 2 on the right, so they cancel. I have 1 calcium on the left and 1 on the right. 2 nitrates on the left and 2 on the right. They are all spectator ions, yeah? Which means really in this reaction, you would get no reaction would occur. They would all cancel each other out. You basically have a beaker of ions floating around and nobody coming together. So you just got these guys basically floating freely in that solution, no solid being made. So if you do have sort of a double displacement reaction where both of the products are soluble, technically speaking, that would be no reaction because you would not get any solid being formed. Any questions on that? All right, I should stop there. I'm having such a nice time, I suppose. We will stop there. We will have our lab coming up, and we are doing chemical reactions. So 14, I want to say. I think it's experiment